Hello everyone, in this video we're going to talk about mutual inductance. Now normally we use the letter M to represent it, and this is the symbol. The symbol is actually made up of the primary coil and the secondary coil with an iron core in the middle. Now what's the function of iron core, you might ask? Now normally iron core will ensure that the magnetic flux from the primary coil concentrated to the secondary coil, so we can see the changes. And normally when changes happen in the primary coil, they will start to induce EMF on the secondary coil. Now you will see this concept of mutual inductance in what we call transformer. Alright, so mutual inductance is the concept that is used in transformer. So this is the basic structure of a mutual inductance. What I have here is a solenoid, and here I have a coil. So this is a primary solenoid, and this is a secondary coil. It also can be primary solenoid and secondary solenoid, or sometimes it can also be primary coil and secondary coil. For the primary, we can see that there's an AC power supply with the switch is open. And here we have only galvanometer and the secondary coil. As the switch is open, there's no current flows in the primary circuit. As we close the switch, we can see that the current starts to flow anti-clockwise. As the current flowing to the solenoid starts to build magnetic field, like this. Here we can see that the poles of the solenoid are south on the left, north on the right. The north is the one that is closer to the secondary coil. According to Lenz's law, the coil will start to repel the change in the magnetic flux. Hence, it will start to produce north pole that is closer to the north of the solenoid. Now, using the right hand grip rule, the thumb will be our north. The forefingers is pointing to this side as the current flows through the circuit of the secondary coil. The needle of the galvanometer will deflect to the left. Just like any other alternating current, it will start to reduce before it changes its direction. As the current starts to reduce, so as the magnetic flux. Even though the south and the north of the solenoid is still the same, but the intensity is changing, and this causing the secondary coil not liking these changes. And again, according to Lenz's law, because it opposing the change in the intensity of the flux, this time the coil will change its pole to south. And using the right hand grip rule, our thumb now is facing to the right. The forefingers now showing the direction of the current downwards to the front. And as the current flows through the galvanometer, it starts to deflect to the right. Let's take a look at the mutual inductance equations. The first one is the mutual inductance for solenoid. M equals to number of turns in primary coil times flux of the primary coil divided by current in the secondary coil, or number of turns in the secondary coil times the magnetic flux of the secondary coil divided by current in the primary coil. Notice that this one is actually magnetic flux linkage. And sometimes we don't have to write this. We can just write this as a symbol of magnetic flux linkage. The next equation is mutual inductance when primary and secondary are coaxial, means that they are sharing their axis. So the equation is M equals to mu naught N1 and 2 A over 2R. Now normally the area is the same size because they are sharing the axis. 2R can also be used as D. D is the diameter of the coil. Induced EMF can also happen in the primary coil. Hence, EMF1 equals to negative M change in the current in the secondary coil. Notice that we still have the negative sign here to indicate that this follows the Lenz's law. The same shape for the induced EMF for the secondary coil is happen when there is a change in the current of the primary coil. Now let's try this tutorial. A primary coil carries a current of 2.5 ampere where the magnetic flux through each turn of the secondary coil due to this current is 3 times 10 to the power of negative 5 Weber. The secondary coil has 400 turns. Now we have to calculate the mutual inductance. If you don't know what to do, it is best if you do the listing first. We're going to use the equation M equals to the flux linkage on the secondary coil divided by the current in the primary coil. So here I deliberately use the flux linkage symbol instead of the N flux. Either way, we're still gonna multiply 400 turns with the 3 times 10 to the power of negative 5 Weber divided by the current in the primary coil. The answer is 4.8 times 10 to the power of negative 5 Henry. Question 2. Two coaxial coils share the same axis where the primary coil has 600 turns with a cross-sectional area of 5 times 10 to the power of negative 4 meters squared. The secondary coil has 900 turns. They both have the mean diameter of 8 centimeters. Calculate the mutual inductance. We're going to use M equals to mu naught N1 and 2 A over, you know what? I'm going to use D instead of 2R's. So the answer is 4.71 times 10 to the power of negative 6 Henry. Let's try question number 3. Two coils have mutual inductance of 0.18 Henry. The current in the secondary coil increases uniformly from 0.5 ampere to 2 amperes in 0.3 second. Calculate the magnitude of the induced EMF in the primary coil. I'm going to use this equation. Don't forget the negative sign. Forget that this is I final. So it is 2 minus 0.5 divided by 0.3. And the answer is 0.9 volt. Now notice that I didn't write the negative sign because the question is just asking for the magnitude. So I don't have to show that this is opposing the induced EMF is opposing the change in the current anymore. This is just a symbol to show that this is opposing. And since the question is asking for the magnitude, I can just leave it like this. No need to add in the negative sign. Let's go to question number 4. A primary coil of 600 turns is placed coaxially with a secondary coil of 900 turns. When the primary decreases its current uniformly from 4 ampere to 0 in 0.02 second, the secondary coil induces an EMF of 27 volt. Calculate the mean radius, right? We have a mean radius of the coil if they both share a common circular cross section. So here I'm going to do the listing. So first of all, I'm going to find the mutual inductance first by using this equation. because I see that there's a change in current. So what I got is 0.135 Henry. Then I'm going to use this one to get our R. R using M equals to mu naught and 1 and 2 A over A 2 R's. Okay, now that we don't have any area, obviously, so we're going to change this one. Instead of A, we're going to change it to pi R squared, like that, because we know that's the equation for the area, the formula for the area. And then what I can see is I can just cancel out like that, the R. Now let's substitute. So the answer for radius is 12.7 centimeters. And the last question, a current of 2 ampere in primary coil produces a magnetic flux of 5 times 10 to the power of negative 6 Weber through each turn of the secondary coil. The secondary coil has 800 turns. Later, the current in the primary coil is increased uniformly 1.5 ampere to 4.5 ampere in 0.06 seconds. Calculate the average induced EMF in the secondary coil. Wow, this is very lengthy. But you know what? To save us, let's do the listing. So my plan is using this two, which is the flux linkage of the secondary coil. I'm going to find the mutual inductance for using the current here of the primary coil. This is from the secondary coil. And then from there, once I got my mutual inductance, I'm going to use M equals negative, what is it? Sorry, EMF equals negative M the current over dt to get the EMF. There you go. That's the plan. So let's do this. The answer for this is 0.002 Henry. Now that we got our mutual inductance, let's find the induced EMF. Change in current. So the answer is 0.1 volt.